So today I would like to talk to you about supermassive black hole studies with the Large Synoptic Survey Telescope. And this talk is not just representing my work, but is on behalf of the whole Active Galactic Nucleus, or AGN Science Collaboration for LSST. And so LSST has been making good progress. It is expected to have a system first light in mid-2021 with full science operations starting in late 2022, early 2023. And among its many science achievements, LSST is expected to greatly advance studies of active galactic nuclei, as you can see in this panel on the right. It should allow us to learn things about active galaxy accretion disks, about the emission line regions, about the torus, about jets, and so on. So what I'd like to do in this talk is start off with a brief review of the LSST surveys from an AGN perspective. I will then talk about AGN selection with LSST as well as multi-wavelength data. I will then move on and talk about some examples of exciting science investigations that can be done with LSST. I will just pick three topics there: variability studies, transient supermassive black hole fueling events, and investigations of active galaxies at high redshift. And then I will end by saying some things about the LSST AGN Science Collaboration. So let's start with this brief review of the LSST surveys. And so LSST, if you had to describe what it will do in one sentence, which will be incomplete of course, is that it will give you a public optical / near infrared survey of about half the sky in the UGRIZY bands to great depths, R of about 27.5 for example, based on about 820 visits in total across all the bands over a 10-year period. And it aims to be a survey that is wide, deep, and fast. By wide, I mean that it will cover the entire observable southern sky, with each exposure made with LSST covering about 50 times the size of the full moon on the sky. It will be deep. Its survey will be 10 to 100 times deeper than that of other very wide field surveys. And it will also be fast. It will be rapidly scanning the sky with these 15-second exposures and thereby providing a color movie of objects that change or move. And clearly active galaxies are known to be variable, so they will fall into the category of sources there that are changing. And LSST can scan the whole observable sky every 4 nights. Now, exactly what its cadence will be is still being settled. I'll say more about that in a little bit. And if you want many more details about LSST, I would refer you to this article by Ivazic et al., which has recently been published, I believe, in the Astrophysical Journal. And here is its archive link where you can get it publicly available for free if you like. Now, LSST is able to accomplish this very impressive survey with specialized instrumentation. Here is a little schematic here on the left showing the light path, and you can see that there are 3 reflections off a primary, a secondary, and then a tertiary, and the tertiary is actually inside and is part of the primary mirror. And then there's also a set of lenses. And all of those optical elements together are what can give you this very wide field of view with high quality imaging. LSST has a 8.4 meter primary mirror, although it will be effectively a 6.7 meter mirror when you account for the fact that the tertiary mirror is carved out of the primary. And again, it will be covering about 10 square degrees with each of its observations, and the optical system will be feeding a 3.2 gigapixel camera, which will be responsible for gathering all of the data. So LSST will conduct a main survey, and here I am showing it as this image, an example operations simulation in the R band of what the main survey may be like. Now, the precise details of the main survey are still being decided. I'll say more about that later, and are subject to change, but basically they are aiming to cover a substantial chunk of the southern sky, this region that is shown here as sort of yellowish and light greenish. That is the main survey area. And the main survey is being designed is being optimized for homogeneity of depth, as well as uniformity of number of visits. They aim to cover something like 18,000 square degrees, and the main survey will use something like 20% of the LSST time. Now, you can see that in addition to the main survey, there are a number of additional surveys that LSST will likely perform. For example, you can see these reddish spots. These correspond to significantly larger numbers of exposures, in fact, much larger in this case, than the main survey. These are the LSST deep drilling fields that have currently been chosen. I'll say more about them momentarily. And furthermore, then, some people would like to get more intensive observations on the northern ecliptic region to study near-Earth objects. They would also like to observe the south celestial pole down here in blue. People would also like to observe the galactic plane, and so on. And I'll say more about those possibilities momentarily. So when the main survey is done, you can hope to have 18,000 square degrees of this. This is a LSST image simulation made by the image simulation team for LSST. It covers about 0.03 square degrees. And so when the LSST main survey is completed, you'll have something like 600,000 images like this one to play with. These will cover 20 billion galaxies and 17 billion stars, and all of these sources will have exquisite photometry, image quality, and astrometry in, again, UGRIZY in many bands, 6 bands. So that shows you what the quality of the data from LSST will be like. Now, in addition to the main survey, as I've just said, there are a number of mini surveys that are being planned or considered. One thing that has been decided is that LSST will conduct more intensive observations of at least 4 so-called deep drilling fields. And here are the 4 fields that have been chosen for deep drilling with LSST. The Cosmos field, the XMM LSS field, the Chandra Deep Field South region, and the Elias S1 region. And what you're seeing here for each of these little sub-images is the LSST field as the large black circle, and then some of the complementary multi-wavelength data that are available in these fields as the various colored circles and rectangles and parallelograms and so on. That's what all of those other things are showing. Now, these fields were chosen to be the LSST deep drilling fields because they already had superb and rapidly growing multi-wavelength data. And that, for example, is critically important for AGN science, given the very broadband nature of the emission from active galactic nuclei. And these fields were chosen years ago and were announced to the community specifically to promote additional multi-wavelength data gathering, especially from facilities with limited lifetimes, infrared facilities, for example, or X-ray facilities, so that these data would be in place for LSST. And that plan has indeed worked. I'll say more about that in a minute. But for example, you can see that the grayscaling in these images, that represents the Spitzer coverage of the deep drilling fields. And a lot of the Spitzer coverage that has been obtained for the deep drilling fields, not all of it, but a lot of it was able to be gathered because these deep drilling fields had been announced and people had a clear priority of observations that they wanted to go make. So again, I'll say more about these deep drilling fields in a little bit, but the LSST project has committed to observing these 4 deep drilling fields substantially more intensively than the LSST main survey. Now, the details of the main survey and of the deep drilling fields and of various other mini surveys is still being settled via a survey strategy optimization process. And I want to tell you a little bit about that right now. The goal of this process is to determine how to observe the main survey and spend 10 to 20% of the LSST time on mini surveys to get the best possible science out of this wonderful new facility that we're going to have. And this survey strategy optimization process is already well in progress. There's a little calendar shown here at the bottom of this slide. There was a call for white papers issued back in July of 2018. Many white papers were prepared by the community and were received in November 2018. These have now been reviewed by the LSST Science Advisory Council or Committee, and they have given a list of recommendations for next step operation simulations runs. And so the idea here is that no decisions have been made based on all these white papers so far. And by the way, here is a list of all the white papers. There were about 50 white papers roughly that were received from the community. No official decisions have been made. What's going to happen is they're going to take the first round of recommendations from the Science Advisory Committee. They are going to run operation simulations similar to the operation simulation that I was showing you back here. This operation simulation to determine if the various proposals for LSST observations that people have put forward in these white papers are technically feasible and how well they indeed achieve the science that the proposers wanted to achieve. And so the idea then is that by early 2020, the project will deliver these extensive simulation results to the so-called Survey Cadence Optimization Committee, and then further work will be done, very likely going back and forth with the community and the people who originally prepared these white papers and so on, to settle on the best possible survey that gives us the best science that we can get with LSST. I will say that this report, this review report prepared by the Science Advisory Committee, is publicly available as of May 1st, and it is well worth reading. If you want to read a useful summary of what people have done in terms of thinking about these white papers, and if you want to read a useful, cogent summary of all the white papers together without having to read all 50 of them, that's a useful document to check out. Okay. Now, I will say that the Active Galactic Nuclei Science Collaboration for LSST submitted white papers as part of this process. We want to make sure that AGN science gets done as best possible. For example, I in fact led the preparation of a white paper on active galaxy science in the LSST deep drilling fields. And in this white paper, the main goal was to specify the best possible footprints for the deep drilling fields to get them exactly right. We've already chosen roughly the regions of sky, but getting the precise pointing exactly right is one thing that was done in this white paper. We also suggested in this white paper requirements for the cadence to give us the best possible active galaxy science. For example, for studies of active galaxy variability. And we also gave requirements on total depths. And in the deep drilling fields, we hope to get a whole lot of observation with LSST. Again, the details have not been settled, but in this white paper, what we propose is to get observations about every 2 nights with the longest observing seasons possible for LSST. And these would be done in a pattern such that there would be 4 30-second visits in U, 1 in G, 1 in R, 3 in I, 5 in Z, and 4 in Y. That's a pretty good filter balance. And then over a 10-year period, you would hope to have something like 900 distinct epochs, each one of them achieving very good depth, as shown in this row here, and you would have 900 visits or 900 epochs of observations in total over the 10 years, achieving these very impressive depths listed down there. So that's one possible idea that is being considered right now for how the deep drilling fields might be observed. I will say that, for example, the Dark Energy Science Collaboration put forward their own ideas on how they would like the deep drilling fields observed, and there will need to be some back and forth to try to come to the best possible solution that satisfies everyone. There was another white paper that was led by Gordon Richards at Drexel, and this white paper explored the effects of the main survey cadence on active galaxy selection and on characterization. In particular, people have been considering these so-called rolling cadences, which you can learn about if you read this Science Advisory Council review report. And this white paper tests the possible effects of rolling cadences on AGN selection and AGN science. And so you can check out that white paper if you want to learn about those various things. Okay, so now let's move on to getting closer to science. Let's talk about active galactic nucleus selection with LSST as well as with multi-wavelength data. So LSST by itself will be able to select active galaxies with a variety of approaches. One thing it can do, of course, is it can do multicolor selection using the UGRIZY bands, which again should have truly superb photometry with excellent depth, very high signal to noise. And that should allow us to effectively select active galaxies from redshifts in the local universe all the way out to redshifts of about 7.5, going out to the Y band. This will be mainly ultraviolet excess selection below redshifts of about 2.5, and you will then be utilizing the Lyman alpha forest at higher redshifts to select active galaxies. And clearly this approach will work best when the active galactic nucleus is substantially more luminous than its host galaxy. Because, of course, in cases where the active galactic nucleus is less luminous than the host galaxy, you will have additional challenges separating out the light associated with the accreting black hole with the light associated with the stars in the host galaxy. And I can say more about that later. Furthermore, you can also utilize variability as another way of selecting active galaxies. In the LSST main survey, in each of the bands, you'll have between 55 and 185 samplings per band over the 10-year period. This will give us a highly effective complement to color selection of active galaxies. And again, we still need to do a better effectiveness assessment of the effectiveness of this selection approach down in the regime where the active galactic nucleus luminosity is comparable to that of the host galaxy. There is some progress there, and I'll say more about that in just a minute. In fact, here is a slide showing some relevant work that has recently been done by Dimitra DeCicco and collaborators, where she has utilized, in this case, deep observations with the VST to perform optical variability selection of AGNs in the cosmos field. And what these two panels compare is an attempt to do active galaxy selection with a 5 months worth of data. And in the right-hand panel, she shows results from a 3-year analysis, where she has 3 years of data. And you go from 27 available visits in the left panel to 54 visits in the right panel. And you can see that as you improve the time span and improve the number of epochs, you get quite effective at selecting active galaxies. All these objects up here with RMS variability deviations above expectations from the noise, shown down here, or from standard non-variable objects, shown down here, are very likely active galaxies, or at least other interesting variable sources in distant galaxies. And DeCicco et al., by comparing her variability selected objects with X-ray selected active galaxies in the cosmos field, finds she is able to reach about 256 active galaxies per square degree. And if you just did as well as she does right now over the full 18,000 square degree LSST sky region, you would get up to about 4.6 million active galaxies selected. Now, we expect that LSST will do even better because, of course, LSST will have a longer baseline, reaching up to 10 years ultimately. You will have more epochs, as I've already said. Each individual epoch will be much deeper and will likely also have better imaging, although the imaging for these data is already quite good. And of course, you will also have more bands available. This work here, by the way, was just done in the R band, although she has additional bands available. This particular analysis is only done for the R band. And so you can see that variability selection, just by itself, should be very effective at giving us, well, many millions of active galaxies in the LSST data set. So then, in addition to variability, one can also utilize astrometry. There, one is ensuring that there is a lack of proper motion from active galaxy candidates, and you can also utilize the effect of differential chromatic refraction. And with the lack of proper motion, well, you will get constraints down to something like 1 milliarcsecond per year at a magnitude of R of 24. And that will be very effective at minimizing confusion with stars, many of which will move over that time span. For example, nearby white dwarfs or nearby L and T dwarfs, things like that, will very likely move at that level. And so this will be effective at discriminating potential interlopers that you might confuse with active galaxies. Okay, so that's the selection you can do with LSST data alone. Now, clearly, it would be crazy to use LSST data alone for active galaxy studies because we know that active galaxies are fundamentally multi-wavelength emitters. And you can see that in this nice example right here of a broadband spectral energy distribution from an active galactic nucleus, in this case, taken from the Chandra Deep Field South region, I believe, at a redshift of 1. And you can utilize the various distinct aspects of active galaxies across the electromagnetic spectrum to improve selection in combination with the LSST data. And there are many facilities that are either already operating or will be operating in the near future contemporaneously with LSST that can be used very effectively for the selection of active galaxies. And in fact, that's what this shows. This shows one of these little time bar chart diagrams, or Gantt plots, I guess, showing the various facilities in the radio here in red, in the infrared in green, in the optical here in blue, and then in the X-ray up here in purple. And the main LSST survey, I guess, would be stopping where this white bar is. And hopefully LSST operation will continue even further beyond that. But you can see that there are many superb facilities ranging from the SKA prototype facilities, ASCAP and Meerkat. You'll have Euclid and WFIRST AFTA in the infrared. You will have, for example, eRosita, as well as all of the archival fields from Chandra and XMM you could utilize in the X-rays. And all of those things can be brought to bear as well to improve the effectiveness of active galaxy selection. And again, for example, you can combine the infrared colors with the optical colors from LSST, and that will be very effective in improving AGN selection, just as one example. Okay, so then, how many active galaxies might we hope to get from LSST in total? Well, to consider that, it's first useful to just get a basic number on the number of active galaxies we expect there to be in the 18,000 square degree main survey area of LSST. And to my knowledge, the deepest, most complete, most reliable surveys of active galaxies to date have been done in the X-ray band. This, for example, shows the number counts of active galaxies in the Chandra Deep Field South. The active galaxies are shown in the blue here. And you can see as you go down to fainter and fainter X-ray fluxes in this ultra-deep 7 million second Chandra observation, the active galaxy number counts down here at the very faintest X-ray fluxes go up to about 23,900 per square degree. Okay, so if you take that number density times the 18,000 square degrees, well, and then consider the optical magnitudes that these active galaxies have, you find that the majority of them should have at least some light detected from them in the very deep stacked LSST images. So LSST will detect something like 300 plus million active galaxies in its 18,000 square degree main survey area. But of course, then the question is, well, how many of those can you actually reliably select as being active galaxies? Just detecting light from something is very different from being able to characterize it and understand what it is. Well, there, one has to consider that obscuration, for example, will make some active galaxies, even some active galaxies that are intrinsically very luminous, not as prominent in, for example, the optical. And so they will not stand out as well, and they'll be harder to select. Furthermore, as I've already alluded to, dilution by host galaxy light will also hinder AGN selection. When an active galactic nucleus only has a comparable luminosity to that of its host galaxy, or even a lower luminosity than that of its host galaxy, that also makes AGN selection increasingly challenging. So what I can say is right now, based on our current considerations of the LSST selection approaches, plus the utilization of all the multi-wavelength data, we feel pretty confident that we'll be able to select something like 20 million of the 300 plus million active galaxies that LSST will detect some light from. So that's like 7% of those, which is pretty good, although clearly we'd like to do a lot better. We hope, especially as the multi-wavelength data get better and better, to select something like 50 plus million of them. And that would give us these truly massive samples of active galaxies with which to select a variety of exciting science topics. And in fact, let's go on to those science topics now. So what I'd like to do now is to give you some examples of active galactic nucleus science investigations that can be done with LSST. This will by no means be complete. And if you want to see more examples of exciting science investigations that can be done with LSST, I will refer you to the LSST Science book, in particular to Chapter 10 of that science book, which describes many of the exciting AGN science possibilities. This is getting a little dated right now, but nevertheless, it still is a very useful reference. And I will also refer you to the website shown here for the LSST Active Galactic Nucleus Science Collaboration. That website lists many other exciting science topics. In particular, I will refer you to the various talk slides that are included on that website, where you can learn a lot more about science possibilities that people are thinking about for LSST. Okay, so first of all, let's just give some basic broad numbers about the nightly LSST supermassive black hole science. Well, every night, LSST, as it scans across, its chunk of sky that it can cover in a given night, will perform monitoring for something like 75 million active galactic nuclei. Now, again, as I've just said back here in this slide, not all of those will be able to be selected as active galaxies, but we feel pretty confident that every night LSST will be doing useful photometric monitoring for 5+ million active galactic nuclei that have been selected as being active galactic nuclei. And of course, if any of these 75 million additional AGNs show interesting prominent variability, LSST will catch that, and we will then be able to identify those new objects as active galactic nuclei. You should also detect many large AGN flares every night, for example, from Quasars or from Accretion-Disk instabilities. The people who work on stellar tidal disruptions, I'll say more about them in a little bit, expect that every night you should discover about 3 stellar tidal disruption events with LSST. You should also discover about every 10 nights a strong quasar microlensing event, and those will be very exciting for studying black hole accretion disks, for example. I'll say more about them in a minute. And you can also hope to find more exotic things, binary supermassive black hole inspirals or mergers and things like that. And then, of course, beyond just the AGN science, of course, there's a huge amount of exciting other time domain science. Every night, LSST should discover something like 2,500 supernovae and 5 orphan gamma ray burst afterglows where the gamma ray burst jet is not pointed directly along our line of sight. And so there should be lots and lots of other exciting transient things being found as well. Okay, so now let's talk about some specific science topics. First of all, LSST will allow truly massive studies of AGN variability. LSST will provide us with millions of well-sampled, accurate, multicolor light curves of active galactic nuclei, spanning a very broad range of timescales, down to minutes and all the way out to 10 years and hopefully beyond. And this entire photometric data set will be made up of billions of photometric measurements. You will, of course, have even better sampling and even better depth for the about 10 to the 5 or more active galaxies in the deep drilling fields. And it will also be possible, of course, to combine the LSST data with data from the Dark Energy Survey and Hypersa Prime Cam and Pan-STARRS and the SDSS to achieve even longer baselines for variability studies. And with this massive AGN variability data set, it would be possible to go and study powerfully general luminosity and spectral variability for AGNs as a function of all sorts of parameters, luminosity and redshift and wavelength and timescale and AGN color and radio properties and line properties and black hole mass and Eddington ratio. Some of those things like black hole mass and Eddington ratio will require at least a single epoch spectra capable of measuring those quantities so you can perform variability correlations with them. But LSST will certainly give you the photometric data required to do that. And people have already found exciting and interesting correlations with these physical properties. Here, for example, is some work by Chelsea McLeod et al. And here she is showing the structure function at long time scales for AGN variability, which appears to decline as you go to higher and higher Eddington ratios. So there is already a pretty clear Eddington ratio dependence of long time scale RMS variability, and it'll be possible to quantify these types of relations much better and to explore the covariance of these various relations with this truly massive data set. You will also be able to identify rare but physically important events that teach us things about the interesting extreme physical processes that can happen in active galaxies. You should be able to identify large instabilities of AGN accretion disks, strong flares of AGN jets, swan song events where AGNs shut off or go down into very low states, quasi-periodic oscillations. These types of phenomena should also be able to be identified to the extent that they exist in this massive AGN sample. Okay, it's also very exciting to consider the prospects for combining the LSST photometric monitoring with time domain spectroscopy. People right now, for example, have been doing extensive time domain spectroscopic studies aimed at measuring black hole masses with the technique of reverberation mapping. For example, there's been a very effective and successful project, the Sloan Digital Sky Survey Reverberation Mapping Project, which is now giving us measurements of black hole masses, direct measurements of black hole masses from the reverberation-based technique out into the distant universe. And there are plans to extend the current Sloan 4 survey in the so-called Sloan 5 project, which has a component called Black Hole Mapper, which has one of its primary goals to perform reverberation mapping of AGNs in 3 of the LSST deep drilling fields. This survey will be operating between 2020 and 2025, and this reverberation mapping-based technique will again look at time delays between when the central source varies and when the broadline region clouds vary in response to changes in the illuminating continuum from the central source. And from that, you can measure the size of the broadline region and thereby deduce the mass of the black hole. That basic approach is going to be utilized in sort of an industrial scale in Sloan 5. And the LSST here will be critical in providing, well, 900 epochs of truly outstanding photometric coverage, which gives you good coverage of how the central source is varying, which you can utilize to improve your reverberation mapping measurements. And so here you are using the combination of the LSST photometry and the spectroscopic observations with the Sloan Digital Sky Survey Telescope to measure black hole masses. There was another project called the Foremost Tide Survey, which will be starting a little bit later than the SDSS-5. They also aim to perform reverberation mapping studies, I believe in all of the 4 currently chosen LSST deep drilling fields between 2022 and 2027. This here is showing a simulation, an operation simulation of the various foremost observations, and you can see the deep drilling fields shown here as these bright spots in our operations simulation. And here are the deep drilling fields, which would be observed very intensively as part of the foremost tides component. Now, in addition to this focused time domain spectroscopy on reverberation mapping, of course, there will be lots of other exciting things that one can do by combining the LSST photometric data with time domain spectroscopic studies. We'll be able to investigate BAL variability, the variability of broad absorption lines, which arise due to high velocity winds flowing outward from active galactic nuclei. It will also be possible to investigate the variability of reddening in active galaxies over time, to identify from the LSST photometry and then follow up spectroscopically changing look quasars, which are another very exciting topic of study right now, as well as to perform general studies of emission line variability. And that's what's being shown here, where you can probe dynamical changes in the broadline region over long time scales by studies of general emission line variability and so on. So again, combining LSST and time domain spectroscopic survey should be very exciting. LSST will also allow excellent studies of accretion-disk structure. People have recently been utilizing this same type of reverberation technique, not utilizing emission line reverberation in this case, but solely looking at the variations between different continuum bands and looking to see how long wavelength continuum bands lag short wavelength continuum bands to deduce the structure of active galactic nucleus accretion disks. And this is some work here by Edelson et al. On 4 very intensively monitored active galactic nuclei that have been observed very intensively with SWIFT. And you can see that the long wavelength bands lag the short wavelength bands, and they do so in a manner such that the lag as a function of wavelength matches fairly well the expectations from AGN accretion disks. From a standard AGN accretion disk that's being illuminated from a small central source, you expect the time delays to follow a scaling law, such a power law with alpha to the 4/3 power. And so that these blue curves here are showing that predicted relation for accretion disks. And you can see that the lag measurements agree with the predictions fairly well in terms of their overall functional form, although interestingly and puzzlingly, the lags quantitatively at all wavelengths are about 2 times too large compared to what you would expect from a standard accretion disk model. And so this is a puzzling phenomenon that needs further investigation, and LSST will be able to perform quality accretion disk reverberation mapping studies for about 3,000 of the AGNs, the brightest AGNs that one can study the best in its deep drilling fields. And so it'll be possible to go and do this continuum reverberation mapping studies of accretion disks in the LSST deep drilling fields very effectively. It should also be possible to perform excellent microlensing studies of active galaxy accretion disks. Here, one would not be using the deep drilling fields primarily. This would be using the main LSST survey. The idea here is that LSST will be monitoring about 3,000 active galactic nuclei that are lensed into multiple images. Here, in fact, shows the predictions of the number of QSOs that should be lensed, okay, as a function of magnitude, and going down to the fairly faint magnitudes LSST will be achieving. You expect to be monitoring about 3,000 active galaxies that are lensed into multiple images. And once LSST identifies these and is monitoring the distinct multiple images and finds evidence that one of the images is varying in a way that's different than the expectations from the others, given the known time delay from the system, that indicates that there is a microlensing event where a star in the lensing galaxy is moving and is changing the magnification pattern down onto the AGN accretion disk. And by unwrapping that whole rather complex process, one can achieve effectively nano arcsecond resolution down onto AGN accretion disks. And if you're interested in reading more details about this rather involved process, specifically relevant to LSST, I refer you to a set of talk slides by Timo Anguita that describes this physical process and how it's relevant to LSST. That's available on the LSST AGN webpage. Okay. LSST will also allow investigations of small separation binary supermassive black holes. Here, the idea is that for supermassive black holes to be able to move from parsec scale separations, where they tend to hang up, you can't really lose more orbital energy due to stellar scattering at that point, and to be able to shrink from parsec scale separations down to milliparsec scale separations, one likely needs gas accretion to remove binary angular momentum. And you can read about this in many simulation papers. Here is just one example of a fairly old simulation out by Quadra et al. And the idea is that the accretion rate onto both of the black holes will likely vary on timescales of the orbital binary period of the two black holes. And you can see these strong variations here in this light curve associated with the black holes orbiting around each other and their accretion changing over time. As black holes traverse from the parsec scale down to the milliparsec scale, well, at sort of 10 to the minus 2 parsecs, you expect these variations to be on month-to-year timescales for reasonable black hole masses. And that's well suited to the LSST monitoring, and such tightly bound binary black holes are hard to find in other ways. And so a massive LSST variability survey should be able to find, or at the least usefully constrain, the uncertain frequency of these very tightly bound 10 to the minus 2 parsec or so binary supermassive black holes. I will, of course, note that already some candidates for these systems are being found, or at least are being claimed. Here is one example here, but the interpretation of these events currently is generally debated. And LSST will provide us, again, with this truly massive photometric data set, so you will be able to do rigorous statistical sample-based studies to constrain this in a quantitative way, and you won't have to worry about false positive effects where you've searched large numbers of candidates and only identified a couple, and then you have to worry, well, what is the statistical significance of this given the number of possibilities that I've checked? LSST will give you a data set where you can just do this rigorously. You will have control of all of your statistical issues so that you can derive reliable constraints globally. Okay. I want to now just say a few words about transient fueling of dormant supermassive black holes. Here, the idea, of course, is that a dormant supermassive black hole can flare up to AGN luminosities for timescales of months to years via the tidal disruption and partial accretion of a star, or alternatively a planet or a gas cloud. And this here shows a simulation of stars coming in, getting tidally torn apart. And here is some of the material that was originally in the star that becomes bound to the black hole. Here is some other material that becomes unbound and is tossed out. And this bound material, when it returns and accretes onto the black hole, is what allows the flare up to AGN luminosities. These tidal stellar tidal disruptions are now being found in wide field optical UV and X-ray surveys. And with LSST, as I had already mentioned, we expect to detect something like 1,000 plus of these systems every year. And you identify them from their fairly rapid rise and then their characteristic decay over time, as well as from the fact that they're often very bright out in the ultraviolet bands and stand out from supernovae in that respect. And so you will need to utilize color cuts and other selection cuts to avoid confusion with all the supernovae that LSST will be finding. But it should be possible to detect many stellar tidal disruption events every year with LSST. You'll be able to then go and measure tidal disruption rates as a function of different galaxy types, as a function of redshift, and so on. You'll be able to understand the diversity of these events. We know that these tidal disruptions have a wide range of luminosities, a range of characteristic temperatures. Some of them launch powerful jets, other ones do not seem to do so. We want to understand why that's the case. With a large sample like this, that should become possible. And we also aim to find remarkable events. For example, white dwarfs should be able to be disrupted, but only by intermediate mass black holes because they're much more tightly bound. And so you need the stronger tidal gravity by passing close to an intermediate mass black hole, which you get for such lower mass systems. So anyway, that's one example of a remarkable event. You should also be able to detect the disruptions of giant planets, of gas cloud captures, and so on. And all of this together will give us insights into the importance globally of transient fueling in terms of the buildup of black hole mass in the universe. Okay, and then finally, I'll just say a few words about the selection of high redshift active galaxies with LSST and associated data. So LSST alone will allow us to detect significant numbers of active galaxies out to redshifts of about 7.5. And this can be done with the characteristic colors that high redshift quasars show. Here is a diagram showing the Z minus Y color versus the I minus Z color for active galaxies or quasars as you go up in redshift. So here's a redshift of 5.7, there is 6, there's 6.5, there is 6.6. And you can see they trace out this characteristic path in a color-color diagram. And one has to be careful, of course, to avoid confusion with L dwarfs and T dwarfs and Y dwarfs and so on, shown with these tracks. But with the various LSST colors, as well as the constraints on proper motion, as well as the multi-wavelength data, and as well as the various follow-up that will need to be done, it should be possible to identify substantial numbers of very high redshift active galaxies. Beyond a redshift of about 7.5, these active galaxies drop out of even LSST's Y band. And so with LSST alone, it becomes very difficult to go to higher redshift still. People have already utilized this technique right now, these techniques right now, to derive the number density of black holes as a function of redshift. And here you can see some nice recent work by Wang et al. 2019, which shows the rapid decline in the AGN number density out at the very highest redshifts, going out from redshifts of 5 to 6 to 7. These things become very rare. And so it takes very powerful surveys to be able to discover these objects in any significant numbers, like LSST. The expected numbers of high redshift quasars, in this case redshifts greater than 6 from LSST, is shown in this plot. Basically, this is work from Reed et al. It shows the number of quasars brighter than this magnitude cut of 23.6, in this case found over a 15,000 square degree region. You can scale that to the exact LSST survey region as a function of redshift. And you can see that, well, at a redshift greater than 6, you expect to have a very large number, something like 2,800. At redshifts greater than 7 from LSST, you should get like 55. And then, as I've mentioned, at redshifts greater than 7.5, at least from LSST data alone, well, you really don't get any because these objects drop out of the Y band. Okay, so that's some yields just from LSST data alone. What is even more exciting, of course, is to combine the LSST data with data from, for example, Euclid and WFIRST. And this plot here from Spergel et al. Shows the LSST photometric depths in the various LSST bands in blue and compares that to the depths from Euclid shown here in Y, J, and H, as well as in WFIRST, which goes much deeper than Euclid, okay, but over a smaller solid angle, like 2,000 square degrees instead of 15,000 square degrees, shown here in red. And by combining, for example, LSST and Euclid, or LSST and WFIRST, one can aim to discover even higher redshift quasars, because you're going out to bands where you still detect the light, even though it's dropped entirely out of LSST's Y band. And the best work that I'm aware of right now that does forecasts for how many such objects one might hope to get is work done by Riz Brandt et al. And this here is a plot that shows some of his forecasts for LSST plus Euclid selection using Z, Y, J, and H. And the predicted quasar numbers, using two different choices for luminosity functions, as you go out to high redshifts are shown here. And you can see that while the numbers become small beyond a redshift of about 7.5, one does still hope to detect significant numbers of AGNs at the high 7s in redshift, even the 8, out to 8.5, perhaps even out to redshift 9 or so. Okay, one can hope to get decent numbers of active galaxies. And so here we will be able to push quasar discovery out to very impressive redshifts, hopefully out to redshifts of 9, maybe if we're very lucky, even somewhat higher. And clearly these will be great objects for studies in a variety of ways. Particularly, I'm excited about investigating these as multi-wavelength targets, investigating their X-ray properties, for example, to investigate the spectral energy distribution evolution of active galaxies out at the very highest redshifts. Now, of course, LSST and WFIRST will be able to discover even fainter systems, okay? Although one has to wonder about whether the LSST data are even going deep enough to, in terms of a dropout sense, complement the WFIRST data. And further assessments of that, I believe, are required. I haven't seen any detailed assessments of LSST plus WFIRST, where I have seen some, like this one here for LSST plus Euclid. Okay, and it will also be possible then to bring in the multi-wavelength data in terms of selecting active galaxies in other ways. LSST plus X-ray investigations should be very effective at finding high redshift, obscured active galaxies. And this is some forecasting that I've done with Fabio Vito, where I show here the solid angle versus depth for a 25-year Chandra plus XMM Newton survey. So if you just imagine mining all of the Chandra and XMM Newton archival fields, assuming they continue to operate out to 25 years, and they're already getting close to that right now, well, they will have covered very impressive solid angles. And in these forecasts, I have screened out observations that are problematic in various ways. Observations that are down in the galactic plane or that are very short, and so on. You can read Brandt and Vito for the details of the screening. But you can see that, well, Chandra will give you, well, the very ultimate in sensitivity, of course, and will give you large coverage out at fairly bright fluxes. And XMM will do even better at covering the bright fluxes, but then, of course, doesn't cover the faint fluxes quite as well. So the two work very well together, and you can get an effective survey over, well, using Chandra and XMM fields together, something like more than 1,100 square degrees. And so the idea here would be to combine the Chandra and XMM Newton source catalogs, especially for their deeper observations, with LSST, Euclid, and WFIRST. And one could also do this with the Rosetta sources, of course. And one could then aim to perform a very effective survey of X-ray selected active galaxies at redshifts of 4 to 8 and over about 1,100 square degrees. And because here you're utilizing the X-ray selection technique, and indeed you're sampling very highly energetic X-rays, very penetrating X-rays out of these high redshifts, you'll be effective at finding obscured active galaxies. And so here then, once you've identified these candidate high redshift X-ray active galactic nuclei based on their photometric colors from LSST, you will then be able to then perform spectroscopy. That will be the only real new cost because the X-ray data are already archival. The LSST data will already be there. All you'll need to do is perform follow-up spectroscopy with the various ongoing spectroscopic surveys to then identify these candidate high redshift active galaxies. And one could then hope to measure the the X-ray luminosity function of active galaxies, including, again, very importantly, including the obscured systems that are not found so well in optical surveys, as well as you could also measure the obscured fraction with something like 500 to 1,100 sources at redshifts of 4 to 6, and 10 to 100 sources at redshifts of 6 to 8. And so this is a way of getting at the obscured AGN population, utilizing all these archival data combined with the wonderful LSST data and making some real headway on this problem without having to wait for the wonderful Athena mission, which is in the more distant future. So one can hope to make real progress on this in the near future just by mining the truly massive archival surveys that have now built up. Okay, so then I would like to end today by talking about the LSST Active Galactic Nuclei Science Collaboration. And again, if you're interested in more details, I refer you to this website, which is the website for the LSST AGN Science Collaboration. And this is the email address for our emailing list, if you're interested in communicating that way. Okay, so the current AGN Science Collaboration has 57 members. Here they are broken down just by country. The majority of them are from the U.S., as one might expect, given that LSST is mainly being funded in terms of its construction in the U.S. Chile also has a significant component, and the U.K., and then there's also fairly good representation here from other European countries and Australia and Canada. And new members have been welcome for many years to join the LSST AGN Science Collaboration, coming from the LSST consortium countries. Now, there have been some recent challenges with this owing to the revised LSST funding model and the revised LSST data policy, as well as some internal reorganization that we're doing right now for the AGN Science Collaboration. And the details of that are still being determined and will become available soon. And you can, again, check the LSST AGN website for updates there. Just to show you some members of the AGN Science Collaboration, here are a couple of photos. This is a photo from, I think, the only real organized meeting we've had where we brought in people to discuss AGN issues. This was done in 2017 January. It was held in Grapevine, Texas. Ohad Shemer was the lead organizer for this meeting. And here are the many participants that attended this meeting. And we had lots of good discussions and started a lot of good planning here in terms of road mapping and science prioritization in this meeting. Here are some additional photos from that meeting. This is where all the serious work got done. This is when we went out to dinner afterwards to a nice barbecue restaurant. And you can see these are friendly folks having a lot of fun AGN discussions here. Here are some of the folks from the UK who are interested in active galaxies and galaxies. This is from a 2017 September meeting that was held in Cambridge, UK. Here are some of the Chilean AGN folks who are working on or interested in LSST work. This was from 2017 December in Santiago, Chile. And so that gives you an idea of some of the people who are involved. And you'll probably recognize some of your friends and colleagues from those photos. The overall organization then of the science collaboration is as such. The AGN Science Collaboration is presently working as a loose confederation. We hope to become a hardcore collaboration, ideally something like a hardcore particle physics collaboration, as the LSST construction proceeds, and we're doing our best to get organized in that way. However, a real challenge there has been the lack of any real funding in the US for such collaboration. It's very hard to do a lot of hardcore heavy lifting real work when there's no money available to support it. And that's something that we are hoping will be improved with the ongoing decadal survey process. But it's clear, everyone knows that there's a huge amount of work that's needed, including on issues including basic AGN selection, where right now you can see we've made some progress, but much better assessments of how many AGNs we're going to get and from which selection techniques are going to provide those AGNs best is something where clearly we need a lot of work. We also need better work analyzing LSST simulations, at doing detailed science planning, as well as working how we're going to pool observational resources. We have so far constructed a roadmap document, the LSST AGN Science Collaboration roadmap, shown down here. Here is the table of contents for that, where we've done a first cut at identifying some of the key tasks that have to be performed to allow this science to be done, and we've done our best to prioritize it. But again, without a lot of funding, it's hard to make for a lot of further progress. Although we have made progress with a couple of approaches. Two successful approaches to date, given that this lack of funding, which has required some creativity, have been as follows. One basic approach has been to kind of bootstrap our way along. That is, do science that has immediate science payoff right now, but which is also getting us ready step by step to deal with the flood of data that will come from LSST. For example, we've been working with the deep field surveys that are available, as well as Stripe 82, and then you can bootstrap your way along to Pan-STARRS, bootstrap your way along to the Dark Energy Survey, bootstrap your way along to the Hypersa Prime Cam, which is probably the data that are most similar to what LSST will be like. And then step by step, you're bootstrapping your way to get closer and closer to what LSST will be like. That's one approach that's had some real success. Another approach, the one that I personally have been most involved in, has been to start gathering the essential multi-wavelength data. That's also something that where you can make real progress right now. You can do exciting science in the short term, and you can also be getting increasingly ready for LSST in the long term. This has been done, for example, with Spitzer, as well as now with XMM Newton, and I'll say a few words about that. For example, once the 4 LSST deep drilling fields were announced, Mark Lacey and collaborators proposed the Spitzer Deep Drill Survey of the LSST deep drilling fields. And he was able, via this proposal, to win additional time to cover the full solid angles on top of the SERVS data, these blue regions, which were already available with good Spitzer coverage. He was able to get very good Spitzer coverage over the full 10 square degrees for the XMM LSS field, the Chandra Deep Field South, and the Elias S1 field. And so those data are already in the can and will be available, and it'll be very exciting to utilize those data in conjunction with all the wonderful LSST data. And that was possible, again, because these LSST deep drilling fields were selected and announced in advance so that there was time to actually get all this done. The Spitzer coverage, of course, as I mentioned before, is showed here as the gray shading in each of these panels. And again, the full LSST field is the black circle in each of these panels. Okay, another multi-wavelength project is coming in X-ray wavelengths. There is an ongoing project that I've been leading called XMM SERVS, which has been getting XMM Newton coverage of the LSST deep drilling fields. In particular, Cosmos already had 2 square degrees of coverage, so we have not yet proposed for more coverage of Cosmos. But what we did do is proposed very substantial additional X-ray observations in XMM LSS, in the Chandra Deep Field South region, and in the Elias S1 region. All of these fields already had some X-ray coverage, but it was either rather narrow field or was too shallow and so on. And so we wanted to bring all of these fields to a uniform, high quality standard in terms of X-ray coverage. And we proposed to cover 4.5 square degrees of XMM LSS, 4.1 square degrees of the Chandra Deep Field South, and 3 square degrees of Elias S1 at that 50 kilosecond depth. And with those observations, we ultimately expect to detect something like 12,000 AGNs and 760 X-ray groups and clusters. And this is a very expensive program. It takes about 5 million seconds of XMM time, even building upon the X-ray data that are already available. And note that even with that very substantial investment, for which we're most grateful, we still have not covered the full LSST deep drilling fields, which are 10 square degrees each. We're covering, almost half in this case, somewhat less here and even less here and for Cosmos. And so additional X-ray observations could be done in principle to cover even more of the LSST deep drilling fields, although that would be obviously very expensive. We already have the data for the XMM LSS all on the ground, analyzed and published. There's a paper by Chen et al., where Chen-Ting Chen did a ton of work on this and did a very nice catalog for the XMM LSS field. Currently, we have incoming data for the Chandra Deep Field South and for ISS-1, and Qingling Ni has already made very substantial progress on cataloging work for the Chandra Deep Field South, and Qingling and Labani Malik are also now working on the ISS-1 field, where the data have come in just very recently indeed. So again, with these data, we hope to do immediate exciting science, investigating supermassive black hole growth across the full range of cosmic environments, and investigating supermassive black hole galaxy connections. And of course, we note that these data have a truly incredible legacy value because they are LSST and dark energy survey deep drilling fields. They are also fields will be very intensively covered with the moons and PFS spectrographs. They are very well positioned for intensive studies with ALMA and so on. So there's a lot of exciting possibilities there. And I will also just mention, of course, that there are many other multi-wavelength and spectroscopic efforts ongoing for the deep drilling fields. I have already now seen some recent really fantastic data coming from the MeerKAT MIGHTY survey, which is getting excellent deep radio coverage of the deep drilling fields. The Toltec instrument on the LMT has chosen several of the LSST deep drilling fields, a few of the LSST deep drilling fields, to get very intensive sub-millimeter surveying coverage. Again, ALMA is already pounding away on these fields some, and will be able to do even more work once there is this general surveying from Toltec. And then there are ongoing spectroscopic surveys. DEVILS is currently getting very intensive observations with the AAT. Moons on the VLT will soon be observing the deep drilling fields. The prime focus spectrograph will also be observing them, and the foremost wave spectrograph will also be observing them. And so there's clearly a huge amount of work needed on this spectroscopic follow-up. And these are some of the facilities that are doing that for the deep drilling fields. And with that, I will end. And so thank you very much for your attention.